is this matrix P0 plus P3, P0 minus P3, P1 plus I, P2, P1 minus I. Now here's the beautiful thing. Look at the determinant of that matrix. What is it? It's P0 squared minus P1 squared minus P2 squared minus P3 squared, which is just P squared, just P mu, P dotted into itself in the Lorentz invariant way. That's very cool because if I take this 2 by 2 matrix and I multiply it on the left by some random 2 by 2 matrix and on the right by the inverse of that random 2 by 2 matrix, the conjugate of the dagger of that 2 by 2 matrix, sorry, then if this random matrix that I multiply it by has determinant 1, the new 2 by 2 matrix that I'll get will have the same determinant as the old one. So that is a transformation that maps one set of p's to another set of p's, keeping the p squared the same. Those are just Lorentz transformations. So that's a way of representing Lorentz transformations. It's the analog of the spin a half, the analog of the way rotations work on spin half particles. So it's the spinor representation of Lorentz transformation. So that's very pretty. You can do that for any momentum, but now something more interesting happens. When this momentum is null, the p squared is 0, that means this determinant is 0, and that means that this 2 by 2 matrix has a single vanishing eigenvalue. Or said another way, it has rank 1. So you can write it as the outer product of a 2-dimensional vector and another 2-dimensional vector. Okay. So here we're just writing it. I've chosen to write the two, don't get scared about this index, it's just saying that this is a 2 by 2 matrix, so A and A dot just run from 1 to 2. And so, but because it has rank 1, I can write it as here's one 2-dimensional vector and here's another 2-dimensional vector. So this is very nice now, because if I hand you 2 of these random 2-dimensional vectors, you can now build immediately a 4 vector, which is null. You don't have to impose by hand that the 0 component is equal in magnitude to the spatial component. And also, Lorentz transformations act very simply. This is 2 by 2 linear transformations on this guy and 2 by 2 linear transformations on that guy. And you can build Lorentz invariants in a very simple way, just by taking 2 of these vectors and taking their cross product. So we denote that by, these are 2-dimensional vectors, so I can take their determinant of the cross product. And the other ones we denote by, these are angle brackets and these with square brackets. So if you remember that amplitude that I wrote down for you with those little square brackets in it, that's what they're referring to. They're referring to these variables, they're called spinor helicity variables. Okay. Now, finally, to complete the introduction to the cast of characters, everything that I talked about so far was just a theory of ordinary gluons, but we can make our life even simpler by going to a close cousin of this theory, which is its maximally supersymmetric version. Now, you can give a whole colloquium on supersymmetry, but it suffices to say that supersymmetry is a new kind of space-time symmetry that mixes bosons and fermions. So if you have a spin 1 particle, you act on it with supersymmetry, you can get a spin a half particle. If you have more than one supersymmetry, you can act twice and get a scalar. If you have 4 supersymmetries, you can do something wonderful, which is to act with a supersymmetry on this negative helicity gluon and turn it into a positive helicity gluon. And that means that we can unify negative and positive helicity gluons together in one multiple. That just makes life a lot easier, because instead of talking about an annoying amplitude with an index which is +1 or -1, depending on the helicity of the particles, we can just label the external states in a much more convenient and nicer way. At this point, supersymmetry is really being used and motivated as a bookkeeping device. And we can actually combine the states, not label them by helicities, by combining them in a particular linear combination that looks like a coherent state, which is a particularly convenient way of doing it. So we really have an object which now depends on lambda, lambda tilde, and these other variables, eta tilde, which are like keeping track of the helicities. Think about it like that. Okay. So these little a's go from 1 to n is the number of particles. Finally, remember that we saw there was a big difference in what the amplitude looked like depending on how many gluons were negative helicity. So when all were plus, it was 0. When all were plus and 1 was minus, it was 0. When 2 were minus and the rest were plus, it was that one-line formula. So something clearly changes. It depends on the number of negative helicities. So it's useful to keep track of how many of the gluons are negative helicity in this object. And that's denoted by this integer k. Just counts the number of negative helicity gluons. Okay. So now we're done. I'm done at least giving you the names of the object we're trying to calculate. But just so you know, there is out there in the world a concrete function It's an actual function of lambdas, lambda tildes, these helicity variables at loop level, the function of these unknown loop momenta. Okay? And so it's sitting there. There's an actual function out there. One way of calculating it is to do unitary evolution through space-time using Feynman diagrams. You can do that, and it's the 80 pages already in the third simplest case. So what we'd like to do is find another way of calculating it, okay? And which doesn't use unitary evolution through space-time. And if we do it in a convincing way, we'll start to understand from the second starting point how it is that we can read off that it could have this other interpretation in terms of unitary evolution through space-time and understand where the space-time and the locality come from. Now, at this point, I should emphasize one of the really nice things about the subject is that it's a highly data-dominated and data-driven subject. That's a little funny because I haven't shown a single experimental plot so far. But it is data-dominated and data-driven. Of course, it's a funny kind of data. It's dominated by theoretical data. What do I mean by this? If you come along with a new whiz-bang way of calculating scattering amplitudes, one thing you have to do is agree with every amplitude that anyone has calculated in the last 60 years. So there's a gigantic number of those, and you would better agree with all of them. Okay? So that's some data that you have to manage. Something else that you have to do is, hopefully you're going to calculate things that have never been computed before. I'll show you some examples. Okay? How do you know you're right? You know you're right because since you're not calculating with Feynman diagrams, it is a huge consistency check that the thing that you get satisfies that it's local and that it's unitary. Okay? That's a massive consistency check. And we apply those consistency checks all the time and they pass all the time. So that's what I mean by being data dominant. You can't screw up in this subject, okay? Or you know when you screw up. And you can't decide that the three-loop calculation is too difficult and maybe the answer is determined by the anthropic principle. Okay? These calculations, they have concrete results. There's nothing you can do about it. So you can't move the goalposts. You either compute something or you don't. All right. So let me just show you what some of these amplitudes actually look like. Because it's a data-dominated subject, as with other data-dominated subjects, big advances happen when new technologies are developed. In this context, new technologies developed means someone comes along with a new way of calculating amplitudes that you couldn't calculate before. Okay. And when that happens, you can then get lots of new data and stare at it and try to see if there's patterns and try to figure out what it's telling you. And see if it comes from some deeper principles. In this case, the big breakthrough that drove a lot of what I'm talking about, there have been many of these things in the last 5 years, but the big breakthrough that happened around 2005 was the development of a new set of methods known as the BCFW recursion relations. After Ruth Brito, Freddie Pichazzo, Bo Fang, and Ed Witten developed this powerful set of methods that calculate those tree amplitudes, those simplest amplitudes, the tree amplitudes, recursively, so that you could, starting from simple amplitudes, you could sew them together and build higher point amplitudes. These methods were extremely powerful. I told you in 2004, you could go up to the 8-particle amplitude that's in some supercomputer in CERN. As of 2005, anyone could have on their desk a 15-point amplitude, and you could stare at it. It was just a massive, massive advance. In fact, you had all of them. You could really have all of them. Just a question of sitting around, and maybe you could hand it to Mathematica and just go away, come back and have the 12-point amplitude sitting under your desk and just stare at it. And it was human digestible. And it led to many, many other important insights. I'll tell you about some of them. It also, I should say, has immediate practical relevance. So many of the tools that actually calculate backgrounds at the LHC, now I think the majority of the actual computer code written by serious people who actually have to get the answer right use the BCFW recursion relations to compute the tree amplitudes. So,
10 minutes, okay?
Yes, definitely. I'll be. Yes, thank you. Okay, but I just want to show you what some of them look like. So if we go back to the 6-point amplitude, now let's look at the most generic case, where it's plus minus, plus minus, plus plus, plus minus. So there's 3 plus and 3 minus. BCF and W computed it and found it as essentially a single term with 2 images just cycled over. Okay. Now, This is still a pretty simple expression, but one remarkable feature that it had is that this expression, that term all by itself, was not local. Could not possibly be given a local space-time interpretation. Okay? And you can determine that by the kinds of poles that it has. This I won't have time to explain in more detail, but actually just staring at the poles could just immediately tell you that term all by itself isn't local. So this is now getting exciting, because the answer is written in this astonishing three-term, very simple way, not 80 pages, but 3 terms. And it's so simple because the building blocks are not local.
What does it mean to say it is or is not local?
Yeah, okay.
You have space-time variables to look at.
Oh, very good. Yeah. So this is what I will explain it then. So the way you can decide whether something came from local interactions in space-time or not is to see the kind of pole structure that it has. When you do have local interactions, the only way you develop poles is when particles that were virtual can become real. But that happens when a bunch of particles come in and produce something here through a local interaction, and it travels a long distance before it does something on the other side. So the kind of poles that it has as a function of the momenta can only look like something divergent happens when the sum of the subset of the external momenta become null. So all of these poles in black have that feature. But these poles in blue do not. And so they cannot possibly have a local interpretation. So there's 2 interesting things here. A, that the answer is amazingly simple, written in this way, but B, that not only are these objects somehow simple and nice, but they also have to satisfy some very interesting ways that they can be put together. Because there's got to be some patterns in how they can be put together, because these non-local poles have got to cancel when you sum them up to make the whole answer. Now, so that was striking, but then what really convinced many people that there was a real new other formulation at work was a